Hi all, thank you for coming. It's great to see so many curious minds. My name is Miloslav Pojman, and my job is to make the internet faster. I'm very curious, and especially about Python. In this talk, I would like to share with you what my curiosity taught me about Python for loops. You know, the for loops for something and something else. Seriously, we often forget what smart software design is hidden under this statement. After this talk, you should understand what happens under the hood when you write a for loop, and with this knowledge, you should be able to write custom classes that can be iterated over. I will show you how iteration fits into Python data model. You probably know the iter function. What you may not know is what does this expression return. So I would like to start with a quick poll. Who knows what does the iter v is v expression return? Who knows why it could be useful? Please raise your hands. Okay, I see about 5 hands, so it's good that you arrive at this talk. Thank you for your answers. I have one more question for you. Who read the Gang of Four book? Who read Design Patterns, Elements of Reusable Object-Oriented Software? Please raise your hands. I would say one third, probably less. Thank you. The Gang of Four book describes 23 classic design patterns, including the iterator. I would not be afraid to call it the Bible of software design. Martin Fowler describes it as the best book ever written on object-oriented design, maybe even over software design overall. But as we see, many Python developers don't feel the need to read it. And I assume that it's because we do not encounter the problems the patterns are solving. And I think that's because Python solves those problems for us by incorporating the design patterns into the language. The iterator is a great example of that. We use it every day, but we don't see it because it's hidden under the for loop. The design patterns are not something specific to one language. So for motivation, let's look at iteration in other languages. In C++, maps are an equivalent of Python dictionaries. The C++ maps are implemented using red-black trees. I don't want to guess how much do you know about red-black trees, but I'm pretty confident that you don't want to write tree traversal whenever you need to go through map items. And you don't have to, because the iterator does that for you. The code example is quite compact if you consider what logic has to be executed. But it's still longer than it would be in Python because it does not use any special syntax. For comparison, let's look at JavaScript. In JavaScript, there is a for-in statement for iterating over objects. Unfortunately, this statement is almost useless because its behavior is hard-coded and it cannot be changed. If I wrote maps in JavaScript using red-black trees, there would be no way how to iterate them in for-in statement. In C++, we saw iterators without syntactic sugar. In JavaScript, we can see syntactic sugar without iterators. And both of these states are suboptimal. And to be fair, both JavaScript and C++ address that by introducing new syntax which uses iterators under the hood. We should appreciate that Python, since its beginnings, provides nice for loop syntax. And since Python 2.2, since year 2001, the for loop syntax uses iterators under the hood. If you are interested about iterators history, I recommend you to search for David Beasley's talk on that topic. What I found most interesting is that the current model started as a hack abusing sequence indexing. If this has to be a proper software engineering talk, I should start with the serious stuff, the UML. You can see a UML diagram of the iterator design pattern. A very similar one can be found in the Genko 4 book. Do you understand it? Do you like it? Don't worry, it's not as bad as it looks like. First, ignore that there are two rows. The top one is exactly the same as the bottom one. Now, look what's on the left and what's on the right. On the left is a container, aka aggregate, aka collection. The container is the object which holds other objects. In Python, it can be a list, set, dictionary, you name it. On the right is an iterator. The iterator is something you may not see, but what's necessary because the iteration is implemented there. A new iterator is created for every for loop. So the whole UML diagram shrinks to an observation that there is something hidden. That hidden thing is called iterator, and it's created when necessary. Let's look how this is translated to Python. In Python, you can call the iter function, and you will get an iterator from the given object. In this example, you will get a list iterator. When you have an iterator, you can call the next function, and you will get the first item from that iterator. If I call the next function again, it will produce subsequent items. When there are no more items to be produced, stop iteration is raised. The iter function is called once for each for loop at the very beginning. The next function is called once for each cycle of a for loop, plus once on top of that to receive that stop iteration. In Python, there is no way how to check whether some next item is available. You have to ask for it and then catch possible exception. This approach is called EAFP, easier to ask for permission than easier to ask for forgiveness than permission. And some people say that it's not a good pattern, but it's very common in Python, and it's even documented in Python docs. A curious mind should ask, what superpowers does the iter function have? How is it able to create an iterator for any object it gets? And also a curious mind should ask, how does that next function understand to any iterator it sees? Answers to those questions will be apparent if we observe a common pattern in Python data model. In Python, when you call the str function, it calls underscore underscore str underscore method under the hood. If you call the len function, it delegates to underscore underscore len underscore underscore method, and so on. So it won't surprise you that the iter function calls underscore underscore iter underscore underscore method. And the next function calls __next method. Just be careful, in Python 2, they somehow forgot some underscores, so upgrade to Python 3 to get the proper behavior. If you attended some Python talks before, you might have noticed that these double underscore methods are often abbreviated as dunder. So dunder iter, dunder next. Just say these words and you will be cool Pythonista. Python gives us nice syntax like for loops and simple functions like iter. And under the hood, it translates it to method calls to those dunder methods. So we can take advantage of the nice language, and at the same time, we can override almost any behavior of Python data structures by implementing those dunder methods. A curious mind should ask, why do we need iterators? Why isn't iteration implemented in the containers? Isn't it better to have one thing instead of two? I will give you two reasons why that's not possible. The first reason is a software engineering principle called separation of concerns. Let's look at the Python list. I can call the iter function and I will get the default iterator for that list. Or I can call the reversed function and I will get an alternative iterator. Or I can create any other iterator I want. Thanks to separation between containers and iterators, I can implement any iteration order which I will need. The even more important reason for separating containers from iterators is that we have to store state of the iteration somewhere. We have to remember what item should be produced next. In Python, strings or tuples are immutable. Immutability means that these objects can be changed after creation. And when something is immutable, it cannot hold any state. And even if we ignore immutability, it would not be a good idea to hold state in containers, because one container can be iterated in two nested loops, and how would you manage all that state in one class? That's where iterators are handy, because a new iterator is created for every for loop, so there is a place where the for loop state can be stored. I've told you that we need two kinds of things: iterators, containers. What I haven't told you that these two kinds of things have something in common. Both of them are iterables. Both of them can be used in for loops. We all know that we can iterate over a range, but we can also iterate over a range iterator. It's almost useless because the behavior will not change, but it shows that the for loop accepts both range and its iterator. And it can be more useful if I use this construct with an alternative iterator. This is something specific to Python. If you look at Java, in Java, iterators are not iterable. And if you ask, they will tell you it's normal. Even the Genko for book does not mention this trick. So this is Python specific. Let's look how does it work. The trick is quite simple. When you call the iter function on an existing iterator, it returns the iterator unmodified. So the for loop can call that iter function, and it can be sure that some iterator will be returned. But do you remember when I told you that a new iterator is necessary for each for loop? Well, it's not so true, because if you use for loop with an existing iterator, nothing new is created. And we should be careful about that, because iterators are exhausted after their first usage. You loop over them, and then they will not produce anything more. So the code example does not print anything from its second for loop. The first for loop exhausts that iterator. Now, you have enough information to answer my original question. What does the expression iter v is v return? It checks whether the given object is an iterator or not. And it can be useful if I plan to iterate over that object multiple times. Because if I see that it's an iterator and it cannot be reused, I have to convert it to something else, something that can be iterated multiple times. Speaking about iterables, special mention belongs to files. You can iterate over files until you will receive lines in that file. The question is, are files iterators or containers? Can I iterate multiple times over them? The answer is that files are iterators. And the reason is that operating system stores position in that file. So no matter how many iterators you would create, there will be still only one position in that file. Think of standard input stream. If you iterate over a standard input stream, you're receiving lines as the user hits return key. But the user won't retype his input just because you decided to write a new for loop to your code. Now, you should understand what happens when you write a for loop. Let's use this knowledge to write a custom iterable class. Let's write a daterange class. Daterange class will behave very similarly to Python built-in range, but it will produce date instances instead of numbers. The daterange class will need start of the range and the end of the range. And the daterange class has to be iterable, so it has to implement dunder-iter method. And that dunder-iter method has to return some iterator. So let's call that iterator daterange iterator. And this is half of the work. We implemented a container, the left side of the UML diagram. So let's move to the right side, to the iterator. The iterator has to remember state of the iteration. So let's store what date should be produced next. And we have to remember when to stop. Don't forget that iterators are iterables, so we have to implement the dunder-iter method, and that iter method has to return self. To advance that iterator, dunder next is called. The dunder next has to raise stop iteration if the iterator is exhausted, and in all other cases, it should return the current date and advance it by 1 day. That's all. We implemented that whole UML diagram. We have an iterator and we have a container. Was that difficult? Slightly. Can we do better? There's one magic keyword, and that magic keyword is called yield. I can replace the whole daterange iterator class by this function, by this method. when a function uses the yield statement, it's not a normal function. It's a generator function, and when called, it returns so-called generator. Generator is a special kind of iterator. When that generator is advanced by calling next, it runs that function until it encounters the yield statement. And at that point, it pauses the execution and waits for being resumed again by call to next. I can simplify my example even more. Just get rid of the container class. Do you want a date range helper? This is it. Just yield dates from start to stop. You don't have to write any class to create container or something like that. Just be careful. If you don't have the container, if you don't have there the class, you are creating the generator directly. And generators are iterators, and iterators are exhausted after the first usage. So if you want something reusable, use the example before. Generators would be a great topic for a separate talk, or probably workshop. And I don't have time to go into details. So I will give you like one recommendation. When you see a list, think of replacing it by generators. This is some function which reads file and stores its output. If I get rid of a list and add the yield statement, I save 2 lines of code and potentially a lot of computer memory because nothing has to be stored. Or you can replace list comprehension by so-called generator comprehension. Just replace the square brackets by rounded parentheses. You will get something which is one-off, but it does not require extra memory. Python iterators and generators can be piped into each other. You can compose them and build complex data flows which yields item from one to another and don't require any huge amounts of memory. And this is a really powerful construct. The whole async await support, which landed in Python 3, is built as a hack abusing generators internally. By the way, I like how iterators started as a hack above sequences and then async started as a hack on top of generators. So let's sum up what I have told you. In Python, there are so-called iterables. Iterables are objects which can be used in for loops. Each iterable has to implement the iter method. And there are 2 kinds of iterables. The most common type are containers. Lists, dictionaries, tuples, you know. They implement the iter method by creating a new iterator. The iterator is the second type of iterable. Their iter method returns self, and that's the reason why they are exhausted after the first usage. And you have to implement the next method. What's the place where all the work has to be done? On the last 2 slides, I have examples of iterables in those 2 groups. Let's start with containers. We saw that Python collections are containers. Python string types are containers. You can iterate over them and you will get characters in them. Python sorted function returns a list, which is a container. Python 3 range function does not return a list, but returns something which is very similar to list. There are other collections in standard library, and list comprehension obviously returns a list. On this slide, I have a few examples of iterators. We saw the iter function, the reverse function. Many Python built-in functions return iterators. There's a whole module full of iterators called Iterators. We mentioned files and file-like objects. And don't forget about generators, they can save you a lot of computer memory. That's all. Thank you. Thank you for it.
All right, I'll have a question. If you could go back to the slide where you replaced the list building with the yield.
This one?
That one, yes. So whenever I try to do that, the return value of the function changes and I get an exhaustible iterator instead of a list.
Yeah.
Do you have a good hack to change it back if I actually want a list?
I think you can write a decorator which can do that. And actually that's something I thought about because I like, you know, saving those 2 lines of code. So I was thinking about adding a decorator which somehow collects the result and then returns a list. But, you know, you save 2 lines at 1 line and your colleagues won't probably thank you for that.
Right. So we're getting some questions now. Is replacing lists with generators better only for speed and memory? Or are there any other advantages? Is it correct to apply this for those lists that are only used once?
I would say maybe when I return something, when I provide some API, I'm trying to make it as minimal as possible. Because I can always return a list instead of a generator. But I cannot change it backwards. And also it somehow shows your intention. In the file parsing example, it shows that, okay, I'm processing the file as the pipe. The input goes in and it goes out, and it's not stored anywhere. It somehow describes my intention that this function works as a filter, as a pipe, something like that. And I find it slightly more readable. And you can look at the other example. I didn't have enough time to go into details, but the thing is that every line applies some operation. And you can do small steps. It allows you to refactor the code. You probably know all those list comprehension for 5 lines of code. With generators, you can replace it by 5 generators. And because they do not require extra memory, there's almost no cost for that.
Thank you. How can iterators save memory if the data is still held in a container like list or dict?
You know, if you have a list, you need some memory which holds that list as a data structure. And then you need a bunch of memory which stores content of that list. If I use a generator, I need that small piece of memory which holds that generator. But it does not store the items at all. Just when you call the next function, it takes the input from the file and applies some transformation. So there is and returns it. And you process the item one by one. So all you need to have that 1 line of code in memory. You don't need to have the full file, all the lines read.
All right, thanks. Can you pickle a generator?
I haven't tried that, and I hate pickle. And I think that pickle is used mainly because people are lazy. So I would not try it, and I don't try even. And by design not, because as I told, like it does not store the content. So you cannot, you know, you have to read the underlying file, and that file won't be pickled. So I'm almost sure that it's not possible. And even if it was, I would not do that.
Right. And that's all the time we have. Thank you, Miloslav.
Thank you for your attention.